So before talking about how to adapt neural networks, let's just do a few toy examples to see how they could implement sort of classification functions. So let's start with some simple, Boolean functions. So suppose I have, two Boolean variables, x1 taking values 0 and 1, and x2 taking values in 0 and 1. And suppose we want to implement x1 or x2. So let's write down the table for that as to what it's going to be. So x1, x2 taking values 0, 1, 0, 1. And so if it's OR, then basically we have ones everywhere except when both of them take value 0, at which point we get 0, right? So, these are, binary sort of logic functions. But what if we now treated x1 and x2 as real numbers and see what these decisions correspond to in the two-dimensional plane? So let's look at that now. So let me draw x1, x2 as real numbers, and I have only these 4 possible things that it could take. At 0, 0, I'll get value 0. At 1, 0, I'm going to mark it as a star. I'll get value 1. At 0, 1, I'll get value 1. I'll mark it as a star. And 1, 1, again a star. So I'm basically writing star corresponds to 1 and this dot corresponds to 0. So that's the kind of decision I want to make. And then I can ask, okay, can a neural network do that? Right? So if I look at just a single neuron, what can it do? It can do something like W1 x1 plus W2 let me see, I need to erase that, plus W2 x2 plus bias through some nonlinearity psi. That's what a single neuron can do. And if I want 0-1 decisions, it seems to make sense that I would choose this, and just a single neuron, if I can actually do it. The sigmoid is a very useful function because it asymptotes to 0 and 1 like this, right? 1 and 0, and it happens really fast. I mean, if you do I'll encourage you to go compute it, but just let me mention that say sigma of 5 is like 0.99. Sigma of 10 is 0.99995 or 6, I think, right? And of course, sigma of minus 5, it's symmetric around half, is 1 minus sigma of 5. And then sigma, so basically it's, and sigma of minus 10 is 1 minus sigma of 10. And these are, close to 0. So what this means is that if the sigmoid, if you feed the sigmoid some value that is, decently positive or decently negative, it'll spit out something that is decently close to 0 and 1, respectively. So now let's go back to our problem of implementing the OR. When you look at that picture, the stars are the ones and the dark dot is a 0. Can you separate the ones and zeros by a line? And yes, it's pretty clear that there's a bunch of lines that could do it. I'll draw a line kind of in the middle of these guys. And what is that line? It's basically x1 plus x2 minus half is 0, right? This particular line that I've drawn, you can see that the x1 intercept and the x2 intercept are both half the way I've drawn it. Again, I could move this line around and still separate these points, but yes, certainly this line works, right? And the ones fall in the following region. x1 plus x2 minus half is bigger than 0. That's this region. And the zeros fall into the region x1 plus x2 minus half is less than 0. So, which means that if I feed this positive enough values of something that's positive enough when x1 plus x2 minus half is bigger than 0 to a sigmoid, I'll get a 1. And the other, if I feed somewhat negative enough values in this region, x1 plus x2 minus half less than 0, I'll get a 0. So one way of implementing these lines then is to just multiply these functions by some factor, say 10 or something like that, right? So x1 plus x2 minus half going into a sigmoid. Let's look at the sigmoid, sigma function here, x1, x2. Instead of x1 plus x2, let me just put a factor of 10 here. So 10x1 plus 10x2. And so I had a minus half there. So maybe when I multiply that by 10, I'll get minus 5. And that will be the output. And what does that give me? So let me call this y hat, which is a sigmoid of 10x1 plus 10x2 minus 5. Well, what is this guy? When x1 is 1 and x2 is 0, this is sigma of 5. So this is equal to sigma of 5 for x1 equals 1, x2 equals 0. It's equal to sigma of 5 for x1 equals 0, x2 equals 1. And when both of them are 1, it's 20 minus 5, sigma of 15. So let me write it here. Y hat is sigma of 15 for x1 equals 1, x2 equals 1. So all of these guys, so basically y hat is approximately equal to 1 for the 3 star points, which is good. And when x1 is 0 and x2 is 0, then y hat is what? 0 plus 0 minus 5, sigma of minus 5, which is approximately equal to 0. So you can see that that's implementing the right function. Then of course you could, if you wanted to be closer to 0 and 1, you could increase the weights proportionally again. So basically instead of 10, 10 and minus 5, you could have 20, 20 and minus 10, right? So that would work even better. 20, 20 minus 10, x1, x2 coming in. So this is going to be even better for implementing OR. Okay, so let's do one more example that is very similar. Let me see, say x1 and x2. Again, x1 and x2 are Boolean variables. So let's write down the truth table. X1, x2, 0, 1, 0, 1. And will be 0 everywhere except when both of them are 1. So you have this truth table. So it's kind of like a flipped version of the picture we had before. And again, if I think of x1, x2 as real values now, you have basically, if I continue to call the ones as stars, I have a star for 1, 1 and 0 for the other 3 points. This is not quite drawn to scale. Okay, and again it's pretty clear that I can have a line, or actually many different lines that can separate the 0 point from the 1 point, right? So let me switch pen color to red and draw one particular line that kind of splits it like this. And you can see that pretty easily that this one is the line x1 plus x2 minus 3 over 2 equals 0. And so 1 happens when x1 plus x2 minus 3 over 2 is bigger than 0, and 0 happens when x1 plus x2 minus 3 over 2 is less than 0. And once again, you can do it exactly the same way, you just multiply these coefficients up by the factor you want in terms of getting to a close enough to 0 and 1, and you get the answer you need. So you have this you have the sigma here, and x1, x2, and the bias. And let's say this, if you are multiplying by a factor of 10, then you have 10, 10, and minus 15, and that is your y hat. And you can check again that you basically get, when both of them are 0, you get sigma of minus 15. When one of them is 1 and the other one is 0, you get sigma of minus 5. This is for 0, 0, and this is for 1, 0, and 0, 1. And for 1, 1, you get 20 minus 15, sigma of 5. So you get sigma of 5 for 1, 1. So this is my y hat for all these cases, and this is my x1, x2. Right? So you can basically get something that is close to 1 in the right places, and these are close to 0. Right? So that's what you get. And again, you saw that the 0 and 1 point here could be separated very simply by a line, and the sigmoid just sort of accelerates the rate at which you go to 0 and 1 when you are falling to each side of the line. So you can see the nonlinearity is pretty important here, right? Now let's take another somewhat more complicated example, as it turns out, and that's x1 XOR x2. So this is the XOR, means it's 1 when exactly one of them is equal to 1, and 0 when they agree in sign. So let's write down the truth table for that. x1 x2 when 0 1. So when both of them are 0 or both of them are 1, the XOR gives me 0. And when exactly one of them, when they disagree in sign or in value, then you get a 1. And again, let me treat x1, x2 as real valued quantities, and putting the stars down for 1, I get a star here and here, and I get zeros here and here for the 1, 1 scenarios. And now it's pretty clear that a single line cannot separate out the zeros from the ones. But you have a choice of lines, right? Let me pick one possibility. I can put a line like this and another line like that. And again, I'm drawing these things in the middle. As you can see, I can move those lines around and even change the slope slightly, and it will still work. But you need these two lines, and I have to be here or here to get a 1, and I'll get a 0 otherwise, right? So basically, I basically need a couple of neurons for implementing these lines, and then one more neuron to say that if I'm on the if I'm either on above the first line or below the second line, I'll get a 1. So let me write down the equation for these regions. This one is x1 minus x2 minus half being bigger than 0. That's this side. And the other side is x2 minus x1 minus half being bigger than 0. And if either of these is true, then I'll get a 1 on the XOR. So as before, I can write these each of these lines I can implement using a sigmoid. So I have a sigmoid and x1, x2, and a bias coming in. So if I multiply everything by a factor of 10 like I've been doing, I'll get 10, minus 10, and minus 5 for the first one, for this guy. And the other one is going to be flipped around, minus 10, 10, and minus 5 for this guy. And then when I, so this one, now I have to take basically an OR of these guys, and I know how to do that also, right? I mean, OR I have done before. What was OR? Or if I did a factor of 5, look like this, 10, 10, and minus 5. So I'll do that. So I'll put these together into a sigmoid, and I'll put a bias of minus 5 here, and I'll put 10 here and 10 here and get a y hat. And you can check that this is approximately, this y hat is approximately equal to x1 XOR x2. So the main takeaway from this is, as soon as you start going to more complicated functions, you need more than just a single line. And so you have this. This is a. Let me change pen colors. So this is a hidden layer. We know that basically one hidden layer with enough neurons is enough to approximate any function. But in practice, of course, deeper networks do turn out to be better. The other takeaway from this simple example is that the moment you have a hidden layer, you can have different ways of doing the same thing. So let me draw the same picture again of what we want, the points we want to separate. So I have the 0 points and the 1 points. And I was separating them before using those two lines that we saw. And let me change pen color again to red to show you two different kinds of lines that will do the same job. This and this, right? This also separates the 0 and 1 points, but these lines look quite different from the earlier ones, right? So immediately, even in this simple scenario, you see that there's different ways of realizing the same function, end-to-end function, and depending on where you start, if you're training a neural network, you can end up in very different places potentially. So even the simple example is pointing out the possibility of local minima. The other thing I wanted to point out is, again, in this simple case, I can tilt those lines around a little bit while keeping the points on the correct side of them. So again, there is not necessarily a unique solution to these things. So as you go to more complex deep networks, you can imagine that the set of possible solutions goes way up, and really you'll be very sensitive to initial conditions and training procedure as to where you end up, which is why training large neural networks still remains somewhat of an art, even though we have made so much progress.